said to Francis, I think, if you can't think of what physics to do next, then invent some new technology. You will find some new physics, and indeed that was the case on Gravity Probe B. I will have to tell you that as the former program manager of Gravity Probe B, I was often called upon to defend the use of public funds for something as esoteric as a measurement of Einstein's relativity. And I think the case for its defense is pretty compelling and pretty easy. I would always say, look, even if you're not interested in the science result, even if you're not interested in the educational result, this 100 PhDs and so on, then you at least ought to believe that the technologies that were invented in the course of Gravity Probe B's development will pay dividends, economic and scientific dividends for decades to come, enormous dividends. But even above the level of a practical or economic argument about it, I would say that when you take on something as challenging as Gravity Probe B was, and you're facing very long odds when it comes to the technology, very long odds when it comes to even succeeding programmatically, and you accomplish it, then I think it's a reminder of the sort of greatness that humans can get to when they put their hearts and minds on an objective like this. And so I think GPB is about science, it's about technology, but it's also about a triumph of the human spirit in the end. With that, I'd like to turn it over to my good friend and colleague, Dr. Colleen Hartman, to talk about the history of GPB.
Thanks, Rex. 5 decades after it was first conceived, today we're celebrating the results of the Gravity Probe B experiment. Testing Einstein's most compelling contribution to humankind is not just a technological marvel, although Rex makes a rather good case for that. It's also an engineering and management case study that's worth a closer look. So my job is to give you a brief history of GPB. A half-century ago, 2 men had the same idea, to use rotating gyroscopes to test general relativity. And Dr. George Pugh, who is with us today, had the idea of using a gyroscope in space, in low Earth orbit, pointing at a guide star in a completely drag-free environment, so no other forces would impinge upon it. So basically, you have a rotating top that you look at its precession or how much it wobbles. He published his results in 1959, and he was working for the Institute for Defense Analysis, and he was an MIT professor. So this idea was published in a DoD publication. He also recognized in this publication the application that drag-free technology could have for us, including in areas of aeronomy, geodesy, satellite navigation, and modeling the Earth and other planets. Meanwhile, Leonard Schiff had the very same idea, and he published his idea in 1960 in Physical Review Letters, the very same place where 51 years later, today, we're announcing the test results of GPB that Francis and his colleagues are publishing. The 2 men learned of each other, and they did something rather quaint and old-fashioned, if you forgive me, Dr. Pugh. They wrote letters to each other, and eventually they exchanged manuscripts. So now we go up to about 1963, a couple years later. NASA begins funding Stanford to think about this idea, and that low level of funding goes on for 2 decades. To give you a passage of time, during that 2 decades, NASA launches puts men on the moon, launches a probe to Mercury, launches the Voyagers to do an outer planets grand tour and beyond, conceives of, builds and launches the shuttle, and begins to build the International Space Station. Then in about 1984, NASA actually funds Stanford to begin building the GPB experiment, and now it's a real project. At about this time, Stanford subcontracts to the Lockheed Martin Corporation for their aerospace expertise, and the Marshall Space Flight Center comes on board to add their engineering expertise to the team. The idea here is to make a shuttle test flight of some of the most important components of GPB for a shuttle acceleration environment, to be followed 2 years later by a shuttle flight of the Free Flyer. The 1986 Challenger disaster changes all of that. The plans are scrapped, and now GPB will go directly to flight on a Delta II. So in rather quick succession here, Lockheed Martin produces this giant thermos bottle, the Dewar, the probe, the satellite. They're delivered to Stanford University. The experiment, this amazing 4 ping pong balls, if you will, coated with niobium that can be levitated or integrated in it. It's tested. It's shipped to Vandenberg Air Force Base, where it meets that 1-second launch window on April 20th, 2004, and has the regret of the PI then looking at it going away from him. After several more years of data analysis and data collection and excruciating data analysis, that brings us to the celebration and the event today. The last decade has seen the development of exquisitely sensitive instruments, new instruments that are able to probe our universe, and we have received surprise after surprise. When carefully tested, some laws that we considered sacrosanct, some laws of physics, have been found deficit. So the weakness of the gravitational force means that general relativity has not been as thoroughly tested as some other theories of fundamental physics. And that's why this test result is so important. Now, even given that, I would say to me the most important thing about GPB are the people who touched it and whom it touched, especially the students. And it really is a who's who of America. So I'm just going to name 2. Sally Ride worked on GPB, and Eric Cornell was an undergraduate student on GPB. He did his senior honors thesis on it. And apparently he was so inspired, he continued in the path of physics to one day recreate an Einsteinian prediction of a state of matter, a Bose-Einstein condensate, for which he won the Nobel Prize. So let's return now to the thoughts of the most famous patent clerk in the world. I think he would be very proud of the tenacity of this group of researchers. And I also think that he said something of himself that applies to the researchers, scientists, engineers, technicians, and support staff at Stanford, at Lockheed Martin, at the Marshall Space Flight Center, and to my colleagues and friends of GPB here at NASA headquarters. Einstein said, "It's not that I'm so smart, it's just that I stay with a problem longer." So now I'd like to introduce Dr. Clifford Will, who is a physics professor at Washington University at St. Louis, and also the head of our external review board for GPB.
Thank you. Well, I first want to describe the role of the Science Advisory Committee for GPB. The SAC was formed in 1998 at NASA's request to help ensure that the final scientific result of the experiment would be of the highest quality. The SAC consisted of 6 eminent scientists, including 1 Nobel laureate, plus me as chair, all independent of GPB and each an expert in a specific area relevant to the mission, from low-temperature physics to data analysis to general relativity theory. 2 members of the SAC are in the audience today. Over a period of 13 years and 20 SAC meetings, each lasting 1 to 2 days, we reviewed the progress of the mission, we criticized, we suggested alternative approaches, and we vetted. We critically reviewed drafts of the just accepted physical review letter, twice. Our charge was to ensure that whatever result emerged from the experiment, it would be credible to the scientific community and that the way it was obtained would be clear and transparent. In the unanimous opinion of the SAC, the GPB team attained this goal. Indeed, in our opinion, the effort of the team in obtaining the result you have heard today has been nothing short of heroic. Faced with the discovery during the final month of post-mission tests that anomalous motions of the gyroscopes were being induced by stray patches of electric fields on the surfaces of the rotors and on the interior surfaces of their housings, they found truly ingenious and innovative ways to pool all the available data in order to understand and map out these anomalies. They did this so well that they could still measure the tiny frame-dragging precession. This detective story, as Francis puts it, is an excellent example of how physicists solve hard problems. Solving this problem is in part why it took over 5 years of data analysis from the end of the mission to reach the announcement today. I would like to remind everybody of the importance of testing fundamental theories of nature. Even though it is popular lore that Einstein was right, I even wrote a book on the subject, no such book is ever completely closed in science. As we have seen with the 1998 discovery of the acceleration of the universe, measuring an effect contrary to established dogma can open the door to a whole new world of understanding as well as of mystery. The precession of a gyroscope in the gravitational field of a rotating body has never been measured before today. While the result in this case does support Einstein, it didn't have to. Physicists will never cease testing their basic theories, whether in order to confirm them better or in order to reveal new physics beyond those standard theories. In some realms, the only place to do this, to carry out such experiments, is in space. This was the case with GPB. Another central aspect of the scientific method is the publication of the results of the research. The physical review letter that has just been accepted gives the merest outline of GPB and how the result was obtained. GPB will truly be completed only when the full details of the experiment are published in the open, peer-reviewed literature. Measuring the frame dragging effect caused by the Earth's rotation also has implications beyond our planet. The incredible outpouring of energy from quasars along narrow jets of matter that stream at nearly the speed of light is most likely driven by the same frame-dragging phenomenon about which you have heard today. In the case of quasars, the central body is a rapidly rotating black hole. In my own current field of research, gravitational wave astronomy, the final in-spiral end merger of two spinning black holes involve truly wild gyrations of the body's spin axes and of the orbit, again driven by the same frame-dragging phenomenon. And these motions are encoded in the gravitational wave signals that we hope will be detected soon by laser interferometric observatories on the ground and in the future by a similar observatory in space. So there is a strong link between gravity probe B and some of the most energetic and cataclysmic events in the universe. Thank you.
Thank you very much, Clifford. I'd like to go ahead and move on to the question and answer session, if I could. Just a reminder for those in the audience, we do have a microphone coming around, so just wait for that. And please identify yourself and give your affiliation. For those that are joining by phone, you can signal the operator that you have a question by pushing the *1 keys. And so let me just check with the audience and see if there's any questions to start. Yes, please, Frank.
Frank Mooring with Aviation Week. I wonder if someone could give a little bit more elaboration on how the noise was worked out of the equation and some idea of the degree of confidence that it was done successfully. Thank you.
So I should say on that.
Francis,
Yeah. First of all, we discovered two things, one during the science mission itself, gathering the science data, and second during this calibration phase. During the science gathering, we discovered that the gyroscope was gradually changing its direction, not of spin, but of its body with relation to the spin axis. It's like a football spinning initially about the wrong axis and then gradually becoming aligned or whatever. So we discovered that. Then we discovered that there was a disturbing effect from pointing off by, which you pointed off to other stars, and we were able to calibrate this as we pointed off to another star and get a reasonably good number. The very interesting thing on that one that came out was we could check the number in two different ways during the data analysis. Now, 3 sets of measurements of this misalignment torque, 1 from the calibration and 2 from the other tests within the data analysis process, all agreed very well to the accuracy needed in the experiment. The strangest of all of the effects rejoices in the name of the roll-pole-hold resonance torque. And here is the phenomenon you observe. we have a spacecraft which rolls to averaging things, and we have a gyroscope that's spinning, and as it spins, it goes through a certain kind of motion which is called pole holding. This is relation to the motion of the Earth's poles. It's analogous. And you were sort of watching 4 gyroscopes. At a certain point, very strange thing happened. Over a course of a day, maybe, one of the gyroscopes moved off to a new position and then settled down. Very surprising. And then another, you'd go on for a while, and then one of the other gyros would do something similar, not in the same magnitude necessarily, not in the same direction, but the same phenomenon obviously was happening. Jeff Kajojek at Marshall Center was a key person in reaching an understanding of this, and what he showed was happening is the slowly changing pole-hold period at certain points reaches a resonance with the rotation of the spacecraft. By the resonance, it's a resonance with something like the 123rd harmonic or something, which no normal physicists ever would believe that you get effects like that. But we were able to verify it, and finally, I like sometimes to say that GPB is a confirmation also of Newtonian mechanics, because we had complete Newtonian explanations of these effects, and the numbers came out right. I don't know whether that helps. I mean, I'm not really giving 5 years of data analysis in 2 minutes, but that's the feeling. Do you want to add something on that, Cliff?
Well, I think another thing that was important was, and this is the kind of thing that experimental physicists do, they take lots of data on a particular experiment, only a small fraction of which may be directly relevant to what they want to measure. But in this case, there was data taken having to do with the very small additional magnetic fields that these rotors obtained. And that data was, in some sense, housekeeping data or junk data that wasn't super relevant to the main mission. But at the end of the day, exploiting this data was really critical to modeling these strange anomalous torques in such detail that they could track the orientation of the spacecraft, or orientation of each rotor with a tolerance of a very small angle over the billions of cycles during which each rotor spun during the mission. So this additional data that was there, they managed to exploit in a really innovative way to thereby build a model that allowed them to take care of these anomalous torques.
Thank you very much. I believe we have a caller on the phone, so if we could go to Adrian Cho at Science. Go ahead, Adrian.
Hi, this is Adrian Cho, Science Magazine. This is a question for Professor Will. I'm wondering how the Gravity Probe B result compares to previous results. There was a result in 2004, an analysis of the Lagos satellites that reported a 10% precision measurement of frame dragging. So I'm wondering how this measurement compares to that measurement.
Right. So this experiment he's referring to is a measurement of the precession of the orbital plane of satellites that are orbiting around the Earth that are tracked extremely precisely with laser tracking. The phenomenon here is the same. It's the dragging of space-time due to the rotating Earth, which causes the orbital plane to also drag around. So I regard these two experiments as rather different ways to attack this same phenomenon. You're measuring how an orbit varies. GPB is measuring how a gyroscope changes. Each involves some complicated data analysis with other sources of error that have to be understood and modeled to get the final result. So there are really two ways of attacking the same underlying phenomenon.
We can just pause and see if there are any further questions in the audience. Yes, sir. We'll get the microphone to you.
Joseph Taylor, Professor of Physics, Princeton University. This is for Cliff or Francis. I'm just curious to know that whether the patch effect difficulty in the end dominates the 20% uncertainty on the frame dragging.
Yes.
Thank you.
Any further questions? Go ahead, Frank.
It's Frank Mooring again. For Rex Gevenden, could you hypothesize some of the or elaborate some of the lessons that may have been learned in developing this spacecraft that could be applied to future spacecrafts, particularly in the context of that quote that you gave about inventing technology to do more physics?
Well, one of the interesting things about the spacecraft that I sort of touched on here was the interaction of the payload with the spacecraft. I mean, normally we have a spacecraft bus that has some sort of generic spacecraft functions, and you put an instrument on there and do things with it. And there's some amount of interaction through data systems and such. But what was really interesting about this one is that the instrument itself was kind of the heart of the control system for the spacecraft. The gyroscopes providing direct feedback into the drag-free part of the system and positioning information and so forth. And the telescope, of course, being not only part of the science instrument but also a guide star. So I think this kind of strong interaction between payload and spacecraft is pretty interesting and might apply to future missions.
Such as?
Well, the things that I talked about, the tying of the control system between the spacecraft and the payload, and using an instrument for a navigation and control function instead of doing that independently on the spacecraft. I mean, it's a very unique case, and so I don't think it's generally applicable, but there are some interesting and subtle things there.
Okay, and with that, we're going to go ahead and end today's event. I just want to thank the panelists for their time today and thank the audience for joining us. As always, you can find out more information about NASA missions and connect with us at www.nasa.gov. So thank you all for joining us today. Have a good one.